Good. Welcome to the lecture today. It's summer begin, or last week was summer begin. You can take a look outside. How do you feel about German summer? But that's another thing. I would like to start with a repetition again from last week. So what did we do last week in the lecture? Yeah? Yeah. Mm-hmm. Very good. So we ended with adhesion, capillary, and solvation force. Can you maybe repeat what was so important or specific or special about the solvation force? The last one. Mm-hmm. 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 Yeah, very good. So there's a structural effect, and there is something special about this theory compared to the other two theories, van der Waals and capillary. And what you described was completely correct, the structuring of the molecules, and this has something to do with the regime we are looking at. So what is the solvation force regime-wise compared to the other two? Did you remember this? Yeah. Can somebody help? Which regime we are looking? What was the special about these different adhesion forces when we look at regimes? What do you think? Yeah? Solvation. Yeah.
It's the regime is individual atoms.
Yeah, free molecular. Yeah.
But for the other two, the capillary and the van der Waals, it's continuous.
Okay, and what is very good? So van der Waals, and at least the model I showed you here, are continuum models. And what is the difference between a continuum theory and free molecular? What is the difference? Yeah? Yeah, what do you mean with arrangement? Yes, but yeah? Yeah, exactly. Exactly. So in free molecular, the atoms, in continuum regime, the atoms just don't matter. They are not considered. And in free molecular, they matter and they are considered and they are part of the theory. And this is why we can describe something like structuring of molecules, right? Okay. But you weren't finished with your review, right? So I think we did more. We finished adhesion and then? Mm-hmm. Uh-huh. So we talked about coagulation, also mentioned in the homework. Very good.
We start with the primary particles and going through a higher maximum aggregation.
Mm-hmm.
And then afterward, we move on to the relatively lower temperature area, and then the agglomerating process
Mm-hmm.
is done, and then aggregation part, we
Mhm.
not distinguish between molecular and then they are connected physical or adhesion forces.
Which one are? That's correct. Which one? Yeah. What is connected in an agglomerate? And how? No, what is connected? What? Not how. No, there are no molecules connected. What is connected, based on what we discussed, in an agglomerate? Particles. Yeah, that's correct. But what is a particle? The primary, the aggregate, the agglomerate. Only the agglomerate is a particle. The primary is not a particle. So, yeah? No, you. Yeah, so the aggregates are connected, and now you can come again. How are they connected? Yeah. No, we cannot say this just. Adhesion forces, yes. But most of the time, van der Waals forces, we didn't make a statement about this. Be careful with this, okay? What is adhesion force for between two particles? What is adhesion force between two particles? So, for example, two aggregates. What is the adhesion force between them? So there are three forces, right? Which one? Yeah. And we didn't make a statement that mostly only van der Waals is holding the aggregates. We never said something like this. And it's for me, from the methodology, how you work with these statements, it's very important that you can make these distinguishes. We made a statement about van der Waals forces when we talked about adhesion force in liquids and adhesion force in gas. What was the statement for van der Waals forces when we talk about adhesion forces in liquids and in gas? Any idea? No? Okay. Do you have any idea? No? You? What is the statement we made when we said van der Waals? So we had adhesion force considering of three forces, and we talk mainly about adhesion force in gas, in air. But we also made a statement what happens if we consider liquids. And then we said something about van der Waals forces. We also said something about capillary forces when we take a look at liquids and when we take a look at gas. What was the statement for these two?
I think if we can predict it from
We can what?
solvation and capillary,
Yeah, what can we do with it?
we can predict the force.
Predict.
The force.
Okay, who agrees that in liquid we can predict the capillary force? What happens with the capillary force in liquid? Yeah? Yeah. There is no liquid bridge because the liquid is everywhere, right? So what happens to the capillary force? There is no capillary force. What is with solvation force? Yeah, again? Yeah, because there is no meniscus, but there are molecules, and the molecules can structure. They can structure in a liquid bridge, and they can structure in a liquid at all. But the meniscus is gone if we put the particle completely in a liquid. What is with van der Waals force in a liquid and in a gas? Think about the statement we made about capillary force. What is with van der Waals force in liquid and in gas? What do you think? You. What do you think? No. G. Yeah. What do you think? Van der Waals force in liquid and in gas. Okay, don't worry. What do you think? You. Yeah. Okay. Who knows? Yeah. Very, very good. The Hamaker constant is different, but the Van der Waals forces are always, yeah, the same, not. Because the Hamaker constant is different, but they are always, compared to capillary force, not constant. What is the capillary force in liquid and in gas? In gas, we already mentioned it. In gas, we have a, yeah, a liquid bridge. And in liquid, so we don't have capillary force in liquid, but we have capillary force in gas. And what is about Van der Waals force? Yeah. Yeah, but we always have it, right? So a Van der Waals force is always there. And that's different, and this is probably what I guess you meant in the statement, but that's different than the Van der Waals force is stronger. We didn't make really statements about these things, and you agree when you say they're stronger in air because there's no material buffering between them. But be careful with these statements, what we can say from the model and what not. And we try to kind of build up which force act when, and this is the distinguishes I really want you're able to do. And the same is with what is a particle, what is a primary particle, what is an aggregate, and what is an agglomerate. And when you just mention the names, like name dropping, then I'm very unhappy in the exam. And I really want you to know what is an agglomerate built up. When you say particles, then I know, okay, you don't have understand it. And when you say it consists of aggregates, oh, good. How are aggregates built up? Primaries. How are they hold together? Solid bridges. Okay, and agglomerate, it's adhesion between aggregates. Okay, this is something we discussed last week. Basically, then one last question. We talked about coagulation related to this. What is the main idea about coagulation? What is the main idea of coagulation or coagulation theory? Yeah? Yeah, very good. Yeah. Yeah. And what is the job of coagulation theory, basically? Everything is correct, very good. So the particles collide, the number of particles decreases, the size increases, and coagulation theory delivers we had it on the board last week. What did we had on the board? Yeah? Yeah, that's okay, but this is already the model and the details. My question is more, what is the general job of coagulation theory? Because everything you described was correct, everything was perfect, but last week I also mentioned what is the idea about coagulation theory? Why we have a coagulation theory? What's the job of this theory? What should it deliver? It gives an equation, but what delivers this equation? Yeah? Yeah, very good. So coagulation theory gives, so coagulation is everything what you described, and the idea of coagulation theory is to describe the amount, the number of particle or the number concentration of particle and how this change with time. Okay, this is coagulation theory. How does the number of particle changes with time. Good. Let's see for today. So today we will talk about experimental methods. Actually, I have some nice ideas how to make this lecture. How to say? I'm still not very happy with this lecture, but I will tell you in a minute why. So the idea of today is that you get a little bit insight into experimental methods we are using in aerosol technology. And in nanotechnology, there's a quite large variety of measurement devices, and depending on which kind of lab classes you already did, or where you put your focus, these instruments can change a lot. And I will just give you basically the insight from my perspective, the machines I worked with, the machines I use or will use in my research, and how they are related to aerosol technology. And most of them are of course, techniques working on particles, right? I'm not so many working on molecules. It's more about working on particles. And another thing, so we are now here, right? So we are quite far in the class. And actually, I figured out that I missed out one date when I planned the class, because I was always having the feeling the class is too short. Yeah?
Sorry, about the coagulation.
Yeah.
You tried the formula for NT over N0
Yeah.
last session, but in your PowerPoint that you uploaded, there is T over 2. The formula is different than we
Yeah.
got in the class.
Take the one from the slide, right? Yeah. If you mention these things in the homework, it's the same as for our exam. So I'm very happy if you mention these errors, and you will, if you take a look, for sure find more errors. And that's fine. And therefore, it's important that you always mention why and where and what you are doing. If you just calculate, it's easy for me to say, okay, it's wrong. But if you just say, okay, I take the equation from there, then I see, okay, you did everything correct, I did the mistake, right? So that's very important that for me also in the exam and so on, it's really important that you always show why you're using a certain equation, where you have it from and so on. And if the equation is wrong, or there are two, even if there are two equations and you use one of them and I have one on the board, the other on the slide, it's not your error, right, at the end. But it's important for me to follow it, because I not always see if I make an error in the equation. Yeah.
Yeah, but the one that you tried was understandable, but this one, the T is divided by 2. I couldn't calculate it. But
Yeah, then take the other one from the board.
on the board is
I didn't. I just was. I saw that there was an error. I didn't check it yet. I didn't have the time. On the weekend, I wasn't there. I cannot give you the answer yet. So if you say no, this one is correct and everything is fine, and then the other I delivered you found an error. That's very good. Then I will correct it. I will take a look at it. I didn't do it yet, so I cannot state it. But if you use an equation which is wrong from me, it's not your fault. So you will not get it from the homework. The mistake, right? If you say, no, I found the error, then just report it to me. I will correct it, and everything is fine. And thank you for finding it. Good. Okay, so we will have one class more, which fits a lot in my schedule, because then we still have a topic I really would like to do, and this is gas to particle conversion, which is a very important topic for me. And then we have two fun topics. And today it's a little bit, how to say, I try to connect a lot of these things now, not on a theoretical, but more on an experimental part, okay? So what we want to do is, measuring is an important part of aerosol technology. So we will not talk about how aerosols are moving today. That's not so important, even if some of the measurement techniques rely on it. But for me, it's important that you realize that measuring is really one of the key tasks you would do in a lab if you work in this field. And we have a lot of different nice, very nice devices. We will also talk about the meaning of the fractal dimension. This is related to measuring. And basically, the emoji I choose this time is not was not randomly chosen, but when I was in Leuven for 3 months doing some research, I worked with a very advanced system and was really proud that I could work with it. And at the end, what I had to do is I had to work with such a PlayStation controller. This is how I made research for 3 months on this super expensive device, because the PlayStation controller was basically the controlling system of this machine. Good. Do you know any measurement techniques which could be interesting for aerosol or and nanotechnology? Any setups you already worked on, you did in the lab? Yeah? Yeah, scanning electron microscope. Did you work on it? What did you investigate it?
Looking at nanostructures.
Okay, what kind of nanostructures? Or what did you were interested in looking at the nanostructures?
Yeah, it was my bachelor.
Mm-hmm.
I looked at the presented paper, the alloy that was gallium.
Okay, so you looked at the alloy, and why? Why you looked at it? Why a SEM? Just for fun, or?
With SEM, we look at the structure. It's the structure that we are.
What structure? The structure of the crystal lattice? The crystals itself, or the crystal lattice? The crystal itself. So you had a porous structure, or?
No, it was the surface of the surface.
Yeah.
By zooming in with the scope, we were able to take particles, which shape they have, which size.
Okay. So it was about shape, it was about size.
They were like built up. So
Yeah.
make an alloy so that this is the alloy something wrong.
Okay, very good. Do you remember which size range you could catch with the SEM?
Yes, it was in the micrometer. But we could go to
Okay, so down to 200 nanometers and micrometers. Very good. Any other ideas? Any other techniques? Any other machines you know which could be interesting for this class? Yeah?
Humidity measurements after the hydrostatic test of pipelines.
Yeah.
And we do this in order to be sure that there is less humidity in the pipeline that is ready for the process. And also humidity measurements again for applying color of the pipeline.
Yeah, okay, that's an interesting point, because humidity plays a huge role, but you talked about pipelines. What is the diameter and size of the pipelines?
From 6 inches to 52 inches.
So they are quite large, right? So this is a technique which is probably not so interesting for us. I mean, it's a nice technique and the humidity is interesting. But what would be our interest in huge pipelines related to aerosol technology?
Corrosion resistance after the processing.
Yeah, but for which kind of field this is more interesting? Sorry?
Oil and gas.
Yeah, coil and gas. So this is really chemical engineering. It's not really aerosol technology, okay? While the humidity is not simple to measure in the case for what we want to do. Okay, so humidity measurement is an important point, but we use a different device. Here we use adsorption isotherms. So we look at particles and we look how water molecules absorb to the particle or leave the surface of the particle. Okay, any other technique? But thank you. Any other techniques? Yeah? Yeah, very good. Actually, I have one with me, and I will show you later how it works. AFM. AFM is my favorite tool, and at the moment I'm on the way to try to buy one. I will show you also later why, but AFM, what can you measure in an AFM? So what could be the relation to this class? Yeah, exactly. So you can measure forces. We talk about adhesion forces. AFM is the tool of choice. What else you can do with an AFM? Only forces? Yeah, size. And also something more I will show you later. What else? AFM? Yeah, surface, yeah. What else? AFM? Another one? Yeah? Yeah, what's the difference from TEM and SEM? Okay, it's more precise. We will take a look why. Exactly, so you talked about 200 nanometers. For these structures, you don't use in TEM. A TEM you use to really look down at 1 nanometer or the crystal lattice in particles or the primaries, really, but not the, as you said, micrometer size structure. The TEM has a different working principle. It's the same family of microscopes, but you make much, much more precise pictures than SEM. Good. So here is in my case, a very important table from a nice book. And in this table, you see an overview about different techniques. And you also see what you can get from these techniques. So we have TEM, SEM, as you mentioned, imaging techniques. And you see here is the primary particle size, the agglomeration size. Do you know what is DF? We already mentioned it in the promising empowerment. What could be DF? Yeah? I didn't hear it. Exactly, it's a fractal dimension. Okay, camera's back. Size distribution, okay, we talked about these things. Shape, and here's also something we didn't talk so much yet, is surface composition and characterization. And there are a lot of techniques, as you see here, which are going towards surface characterization and composition. So FTER, for example, is a technique I really like to do. Does anybody of you worked with FTER? Yeah, where did you do it? Yeah. 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 So basically, what is FTR doing? Yeah. So basically, you can take a look at your surface and it tells you what structures, what molecules you have on your surface or surface groups, right? And if you think, for example, about adhesion, of course, the composition of the surface is extremely important. And since nanostructures are very small, they have relatively large surface area. So the structure of the surface is one of the key points how the nanoparticle or nanostructure interacts with the environment. So you should really, really well know the surface, because if you don't know the surface, if you cannot play with the surface, your nanostructure has only limited use. Also TGA, does anybody of you know what is TGA? Or who worked with TGA? Where? Yeah. Yeah, thermal gravimetric analysis. Mm-hmm. And yeah.
It can be heated up to, for example, 1,000 Celsius.
Mm-hmm.
And we can see the decomposition with the temperature, depending on temperature, how the decomposition of used to the sample composition.
Yeah, so the nice thing is basically, as you said, so you heat your sample and then you see the mass going up from the sample. Do you directly know what is leaving your sample from the TGA itself? So you have a powder and you heat it to 100, 200, 300, 400, 500, and then you have it on a balance, and after time you see that it goes less in weight, because something, depending on the temperature you apply, is leaving the surface. Does the TGA directly tell you what is leaving the surface? No, why? Yeah, there is no detection about it. So what I, for example, do is I take nanoparticles, I make an FTER of my nanostructures, and then I know what is on the surface. And if it's very simple structures, I figure out how this groups. So if you have, in the simplest case, you have water and OH groups, and you know that water, which is basically physically bonded to the OH groups, leaves much earlier the surface than the OH group itself. So depending on the profile of the TGA, you can link the TGA result to, for example, FTER result or other surface characterizations. So what you need to know is what is on your surface, and TGA, for example, tells you how it behaves. And then you also get the amount, because FTER not really tells you the amount of water. And if you really want to know, okay, there is water, how much, then you would work with TGA. So these are all surface surface techniques. Then there is one, it's important, adsorption, desorption, BET. Who works with BET already? That's a pity. Maybe I have to introduce it then in the lab class for here, because I will get now a BET. And BET is a very simple but very powerful tool. And BET is, you take a powder and you put it in a glass pipe, basically, or bulb, and then you apply vacuum on it. And then you address some temperature. I think it's about 200 degrees, because you want to have basically the physical bond water should go away. You want to have a free surface. And then nitrogen goes in. You're pumping nitrogen at different pressures. And the nitrogen will go for different pressures to the surface or not. And from there, you can determine basically the porosity and the specific surface area, because you know how the nitrogen behaves, and you can just count how much goes in and how much goes out, and the difference will stay on your surface of the powder. And with this, you can determine in a very simple experiment porosities and specific surface areas. What can I do with a specific surface area? If I know the surface area of my particles, what can I do with this information very easily? What can I calculate with it extreme? Volume, and with the volume I can calculate? Diameter, exactly. So I get a very easy tool here, because compared to TEM, SEM, or other things, BET is extremely easy, extremely cheap, and a very powerful tool to get particle sizes of powders. Good. Then there is something, XRD. What is, or who has worked with XRD already in the lab class? Yeah, in which one?
Also,
Yeah, inorganic chemistry. How does XRD work? What do you remember from XRD? Yeah?
So basically, it's mostly done for powder.
Mm-hmm.
And X-ray light.
Mm-hmm. So we have an X-ray source, okay. That's different than the other ones. So we have X-ray here. So makes the machine a little bit more complicated, right? Why we have X-ray? To? Excite. Mm-hmm.
Measure the angle.
So basically, what is that the X-ray goes in, And if you have a crystal, the atoms are very ordered, right? So depending on the incoming angle, what will the X-ray in XRD doing here in this case? Yeah? Yeah, very good. How? What? Yeah. Yeah. So because I will also have an outgoing beam, and it could be that, for example, this one goes here, and these distances I can detect, I can calculate, and basically on the angle I will hit different parts and get different informations. And so what information compared to the other techniques I get from XRD? Yeah? Yeah, the crystal phases. So if I have an amorphous structure, or for example, if how the crystallinity, so if it's, how to say, how much percent of your particle is a crystal, and on the other hand, what kind of crystal is it? So TiO2 has different phases. Do you know the phases of TiO2? Yeah? Yeah. And the other one. Anatas and rutil are the main one. And they have different properties. And depending on what you want to do, you can adjust, and this is something we do a lot when working with nanoparticles, we adjust the crystallinity. So for example, by doping, we change the crystallinity because we want to have it, or by doping, we change another property of the nanoparticle, but we want to keep our crystal. And these parts you can discover with or investigate with XRD. And so far, I think I worked with all of the techniques listed here. So when you characterize nanoparticles, this is really a huge variety of very important tools. And why so many techniques? And that's exactly the point. You cannot just work on one or investigate one property. We have so many properties. And depending on the research you are doing, these properties are less or more important, but you always need at least a certain proper characterization of your system. So it doesn't matter what you do with your nanoparticles. You need to know the size of them. Okay? If you don't need the size, even if it's not the important value, but it has to do with characterization of your system. You should know what is on the surface. You should know what kind of phase they are, how they are built up and these things. And if you look at most paper, figure 1, figure 2 are just characterization of the system. And since you have so many possibilities to measure, we need so many kind of devices, because there is not one device which can do all or deliver all these things. And this is a nice comic. I really like it because it's a comic made for the German education system, and it fits quite well to here. So the guy in front is the teacher, and the animals are the pupils. And you see they are very, very different. Like the list of properties here is very, very different. And the idea of the German education system is, it's from the 70s, that they said, okay, I want to have a fair exam, so all of you get the same tasks. Climb on the tree. That's the task. Okay? And that's how the German education system works. You always, all of you get the same task, but here you see if the task is really fair is another question. And the same you can apply to measuring techniques, right? And to the kind of research you want to do with these things. So, again, why so many techniques? And here is powder I investigated. It's titania and alumina. And the first thing I want to do is I want to figure out what kind of powder do I have size-wise. And now you learned we have aggregates, we have agglomerates, and we have primary particles. And from here, this is TEM pictures. It's easy, or it's not easy. So the first thing we always do is size analysis. So which sizes do I can get from this picture? Yeah? Mm-hmm. So what, if you analyze these pictures, what kind of, if you look at this table, what could you get out? Can you say something about agglomerates or aggregates from this picture? Yes or no? Can you or not? No, right? How is about the primary particles? No? Why not? Aggregates and agglomerates, I agree. Primaries are distinguishable or not? What is, for example, this one here? This one. Is it distinguishable as a primary or not? This one here. Yeah? Yeah. Or, for example, here, or here, or here. So primaries, you can count. You just, what you do is you assume spherical size, and then you just put spheres with a software where you're sure this is a primary. Not all of them, you look at multiple pictures, and in this way, you can get primary particle size. And then you get a size distribution, and if you want to be sure, you make an XRD, because XRD gives you also sizes. From the peaks, you can calculate the size of the crystal. It's different to the size of the TEM primary, but you see if you're in the good range. Then you make a BET, and then you see if your analysis is good or not so good. And in the best case, all three methods give you more or less plus minus a few nanometer the same size. Good, but I would like to know something about aggregates and agglomerates because I was investigating here adhesion and also unfolding of nanoparticles, and therefore I need to know how my agglomerate is built up. And by the pictures, I didn't get it. So, but I was able to get aggregates and agglomerates information. So what I need is different techniques. And one technique for agglomerates is that I kind of measure them above the flame. So above the flame, before I collect them, I can, with a laser, or there are also some other devices, measure the size of the agglomerate. But this is a very unprecise number. But at least I had the possibility. Aggregates was easier, because in an aggregate, you take these powders and you put it into a liquid. And then you sonicate it, and by this you break the bonds between the aggregates, but you cannot break the aggregate itself. So you kind of release the aggregates out of the agglomerate, and then you just measure it by DLS or by a centrifuge, okay? And this is, again, really important that you know, okay, at what entity I'm looking here. And aggregates you can measure by destroying the agglomerate and then take a look at the aggregate size. And then you don't measure primaries. Primaries, if you take a look here and count them, or if you make BET, for example. So if we take a look now at TM, TM is what you mentioned, and I don't know if anybody of you has classes with Mertins, yeah, from material science. Okay, because he's really, really an expert in TEM and is doing a lot of nice research, and we also have a TEM here, so he's using it. And the TEM is what you see here. Basically, a beam of electrons is transmitted through a sample to form an image. The image is generated from the interaction of the electrons with the sample as the beam is transmitted through. So in a TEM, you have this electron gun. It's very often a tungsten wire, and you apply a very high voltage, 100 to 300 kilovolt, okay? And then you emit, you shoot electrons from here, and these electrons are then further kind of, I'm missing the word. To check it, what? Focus is focused by the lenses here, could be magnetic or electric lenses, and the sample of the TEM is where's the blue point. Here is the sample. So you have here the generation of the electrons, and in the middle you put your sample, because the electrons, they go through your sample. And this is why you get these very high resolution. It has also to do with the de Broglie wavelength. So the resolution you get depends on the wavelength of your light. This is why an optical microscope is limited, right? The wavelength of the optical light is 300 to 700 nanometer. So with this wavelength, so if you look through a microscope, an optical one, you cannot see 1 nanometer. It doesn't work. But here we have electrons with different wavelengths, and they can go to very, very small structures. So electrons are generated by emission from a heated tungsten filament here. The electron beam is focused by magnetic lenses, and the interior of the TM must be under high vacuum to prevent scattering of the electrons by air molecules. So normally you have 10 to the power minus 4 Pascal. And there are two reasons. One is, if you would have air in there, the electrons you're shooting would interact with the air and you don't get a clear image. Okay, it's the same if I would have a lot of fog in this room and I try to make a picture with a camera. I don't see, because the fog is kind of disturbing my image. And the other thing is that you have an extremely high voltage. And if you have an extremely high voltage difference between your electron gun and the surface, you could get an arc. And you don't want to have such a strong arc in your system. So this is why the higher the voltage you apply here, the higher the vacuum you need in your system. And this can be up 10 to the power minus 7 or minus 9 Pascal. And therefore you need multiple pumps, because it's not, one pump is not able to deliver this high vacuum. And this is also why the sample need airlocks. So you have different airlocks when you load or unload the sample. And now you see that TM is an extremely nice microscope, but very expensive and not as easy as handling. This is why BET is so cool. BET is something I can teach you in 1 hour how to use BET. But after 1 hour, I would never let you alone on my TM. Okay? So. Anything I forgot here? No. One important thing, of course, is because the electrons are transmitted through, the sample has to be extremely thin. So this means you need sample preparation, 100, 200 nanometer. The sample shouldn't be thicker than that. And when you work with particles, you have these TEM grids. They are not that expensive. Sometimes you have this kind of box where you have multiple of them, I think 40, 50 of these grids. Sometimes you have very versatile students who are holding them in this way open and all the grids fall down. So you directly can put it into trash and buy new ones. But they are all the same. They are 3 millimeter in diameter, so they are like this. And in the holes you see here is a very thin carbon layer. And then what you do is you take particles, put them in a liquid, and put a few drops on the grid. So rule of thumb, 10% or less coverage of particles should be on your grid. Then you get good images, because you saw here, if you have everywhere particles, you wouldn't see these. So the picture would be just too crowded. So this is already on the edge, what you see here. The carbon film is in between, so what we don't see here is the copper. The copper, we don't look at the copper, we look at the holes between the copper. There's the carbon film, there you put the particles or whatever. And what is important, when you take a look at these pictures I showed you, you can count the primaries, right? So, but if you count 10 and then you have an 11th one, the size distribution will change a lot. So how many particles do you have to count to get a good statement of your size? And this is what was investigated here. So here is the size, this is the area, and this one is the spread. I forgot the density. I forgot the name for it, but it's the standard deviation, geometric standard deviation of the size distribution. And here you see the number of particles counted, and you see at least if you count something like 400 particles, the size or the standard deviation doesn't change anymore much, right? But if you only count 10, 20, 50, your result really depends on the amount of particles you counted. And this is also something not only for particle size, but if you make any measurement, always be sure if the number you counted or whatever is statistically relevant, okay? If you just count 5 things and then say, that's my number, be sure if 5 is a good number to count, or if you need 50, 5,000, or whatever. And for particle size and TEM, we have a clear knowledge about it. And this is, for example, what I did here. I counted the sizes, and then I get these very nice size distributions. You could make a fit, then it would be log norm, as we discussed in the lecture, because you see it on the scale. And what was for me the important part I want to analyze here is I have titania and I have alumina. And titania and alumina are different in size, so titania is larger than alumina, but what is the same? Very important information for me at this part here. If you look at this right image, what does not change? What does not change in the right diagram? Titania and alumina are different. What is not different? What do you think? What is not different? Yeah?
Primary particle size, same. Outside phobic.
Yeah, what could Flick and phobic be? Very good, yeah? Yeah. So we have hydrophilic and hydrophobic surfaces. And what you do is you have hydrophilic particles and you make a chemical treatment to make them hydrophobic. And I want to investigate adhesion forces, and therefore there should be a difference between hydrophilic and hydrophobic. But I have to be sure that I don't change the particle. Because if I change the particle size, for example, this has also an influence. Because if you think about the equation, the size was in there. So if I change the surface of the particle, I have to be sure that I don't change the particle itself. And this is why I use TEM here, because I want to know the difference between alumina and titania, of course. But it's really hard if I make different forces or measure different forces between alumina and titania. It could be the size, it could be the material. And therefore, it was really important for me that if I compare hydrophilic alumina to hydrophobic alumina, to show the size is the same. For alumina, it's perfect. For titania, it's more or less perfect, but this is just measurement spread, so this difference is not really large. Okay, so here is something else which we investigated in a TEM, and this is now doping. So we have titania, and we put iron in there. And basically, the idea is to play around with the band gap. So we want to change the band gap, lower the band gap of the titania by putting some iron in there. But we don't want to change, the same as in the picture before, the properties of the particles, other than the band gap. So we don't want to change the crystallinity. We don't want to change the size. So here, the TEM helps us to take a look at the particles itself, the agglomerates and the primaries, and then with this is now a very expensive TEM, you can go really to detail and you see how the lattice distances here, what we also see in XRD, and of course you also make XRD to prove, but these distances you see really in the TEM, and you see how the distance from 0.355 to 0.3.2 decreases with increasing the doping. Also the doping decreases the particle size. This is what you see here also. And this is what you have to consider. If you change one variable, you also play around with the other ones. And this could be beneficial, could be, but also very, very bad, okay? And this is why a good characterization is so important. And here also another question, and this is what you also can do with the TEM. If it's well equipped, you not only look at sizes or crystal structures, you also can take a look. So we put iron into the titania, and then we want to know where is the iron in the titania? Is it homogeneously, or did we get segregation at a specific part? Maybe we even get iron oxide. We don't want to have iron oxide. And this is what you see here. So you see that here is Ti mapping. So we see where is the Ti in the TiO2 doped, and here is Fe mapping. So where is the iron? And then you see that the iron is very well distributed in these structures. So we get an information where is the material in our structure. Good. So taking a look at SEM, and you already mentioned SEM. SEM works quite similar as the TEM, but you see the lower half is missing. So the sample you just put on the bottom, and this is because the detection system is a little bit different. Now we look at scattering electrons. So the electrons go, interact with the sample and scatter, and then we have a detector which, so for example here or here, collects the backscattered or secondary scattered electrons. So, and this is a very useful tool and even more simple than a TEM and cheaper than a TEM. SEMs you can buy now, like in the past a computer, this size, you put it on a table, open it and put your sample. The vacuum is not always that high, but there are high vacuum systems which are going to 10 to the power minus 7. And what you can take a look is shape, size, the structure in granular, basically all what you mentioned. And for SEM, you found these really cool pictures. For example, here, somebody is smoking. Who's smoking? I want to figure out. Maybe from there? I don't know. Somebody of you is smoking? No. Because I would be really...
The doors are open.
Yeah, but also in the other lecture room, they shouldn't smoke. Okay, so basically you get these extremely nice images, and with the SEM you can make, and if you take a look in the internet, you find super cool SEM images of all kind of millimeter, micrometer structures. And for us, it's important, for example, if we talk about gas sensors, so we talked about these liquid flame, FSP, flame spray pyrolysis to get nanostructures, and these nanostructures is what you see here, a porous layer for gas sensing, right? Gas sensing, the cigarette smoke. We are, I don't know why, but it's smelling like this. And for example, you get an overview. This is an SEM picture of the sensor you make, but also we just look at the top. And the question is, how is the sensor built up, the sensing layer? So we can cut a hole into it, turn it, and then you see, and this is really interesting, that the structure densifies with depthness. So the porosity changes with height. Okay, this is an extremely important information for a sensor, that the porosity is not everywhere the same, but changing. Okay, if you don't want it, you have to design your process a little bit different. And this is what is clearly seen here. And other thing, and this is the most beautiful agglomerate I made in my life so far, because it's extremely, it looks like from a computer simulation. So if you want to look at agglomerate, the size is not here, but this is, the bar would be, I think, 5 micrometer here, so it's a quite large agglomerate, and the primary size is 10 nanometer, so it's a huge one. And this structure is characterized not only by the size, but also by the so-called fractal dimension. And the fractal dimension is something you see here. So the agglomerate, like this, could have multiple shapes. And basically, the fractal dimension tells us how open the structure is. So if it would be a very dense agglomerate with a very low porosity, the fractal dimension would be high. And here it's a very open structure with all these arms, and then there are smaller arms and so on. So the fractal dimension is very low. And the fractal dimension you can determine by getting the overall size of the agglomerate related to the number of the primary particle and the size of the primary particle. Because the size of the agglomerate and the number and size of the primaries will give you the information. If you have a lot of very small primary particles and you have a huge agglomerate, it means these small particles have to be like this to get the size, right? If the agglomerate size would be very small, all your primaries would be sitting very close to each other because the structure is not that big, right? And this relation is described by the fractal dimension, and there is a very nice example, what I really like, and this is the question about what is the length of the coastline of Great Britain. So this is Great Britain, and the question now is what is the length of the coast here, right? So how we can determine it by measuring it. And measuring is not as easy as you think, even if it's a basic question like the coastline length. And the answer is the length depends on your measurement scale. And I don't know if anybody of you is running, but if you're running and you don't have a watch, but afterwards you want to figure out the distance you were running, you have these maps where you can put points. And there you see that the distance depends on the number of points you're setting. Because if you set not enough points, you just have a straight line, but you were running like this, right? And that's the same principle here. So, on the other hand, you cannot go infinitively small, because how do you measure the coastline if you really measure it meter by meter by meter? How do you do it? Do you walk each meter, or do you look at Google Maps meter for meter? I don't know how many years you will sit there. So you have to find a way, what is the minimum scale and what is the maximum scale you can put on your ruler to get a good, valuable number. And this is very nice seen in this GIF. So you see here the shape, so what is considered, and now you see it decreases and what happens, and now you slowly see it, that the measurement scale changes. It increases and then the distance or the length decreases. Now you see the shape is changing because when you have a larger measurement scale, you don't get all the informations, right? So, and if you plot these two things, the length of the coastline, so the size of the agglomerate basically, and your ruler size, the size of the primary particle, if you put this in a diagram, you get this plot. Here is the coastline length, and here is the step size. So 12 or 15 kilometer, 25 kilometer, and you see that there is in a linear and a log-log scale, you get a linear line. So you can fit it very well. And the fitting parameter, this is the fractal dimension, df. So the fitting parameter tells you the relation between the step size and the coast length, or if you want to have this information, you need multiple of these measurement points to put a straight line through it. So what does it mean? Because it's a dimension, right? Fractal dimension. So what is the meaning of dimension? The meaning of dimension is that we know, how many dimensions do you know in real life? Yeah? 3, right? Length, width, and height. And now we have a dimension with 1.4. It's weird, but mathematically it's not a problem, because if you calculate with dimensions, just calculating, nobody forbids you to put a comma there, right? Why? It's for calculating, it's not it's for us, imaginary, it's a problem. But for calculating, it's not a problem. Basically, the mathematical concept comes from a guy called Mandelbrot, and he discovered, or I think in the 70s, he kind of came with the idea there could be something between 1, 2, and 3, 1.2, whatever. And this was really important for computational powers because the fractal dimensions help the computer a lot. These first graphic systems, they really work with fractal dimension, and this extremely decreases computational power. And it works quite easy because if you have a structure and you have particles and you make a line, and then you only have the option that the structure grows in one direction, right? Or in one dimension. So the only thing I can do is I can put a particle to the left and to the right, and to the left and to the right. And this is a dimension of 1. Okay, it's a line. And dimension of 2, we don't consider 3 in this example, but this is dimension 1, and this is dimension 2. And dimension 2 means I have a structure and I can put particles, and now I have length or width and height. Width and height, okay? So the width and the height. So I will put my particles always like this, and my structure will equally grow in both dimensions. So I have 2 dimensions. But I also could, like you know from snowflakes, for example, I could do it like this. Nobody forbids me to put, and this is also if you think about the agglomerate, right? I take my primary particles, I put one here, I put one here, I put one here, but I will get a lot of empty space. And this means my structure is not one-dimensional, but my structure is not fully two-dimensional. It's between. Of course, we look at an area here, okay? But the structure itself is not the two-dimensional, completely occupied square. And this is a fractal dimension. And this is how we can kind of tell a lot about our agglomerates. Because an agglomerate could be like this. This would be a nanotube, for example. A carbon nanotube has a fractal dimension of 1. And this would be a graphene sheet. It has a fractal dimension of 2. But here we have these porous structures, and porosity for a gas sensor is so for a good sensor, I need a certain fractal dimension in my agglomerate to have a certain porosity. And therefore, it's quite easy. I just need the number of primary particles, the radius of the agglomerate, and the diameter of the primary particles. And then I can calculate df, which is the fractal dimension. So for me, it's extremely important, but it's also important because I don't know if you had this concept in another class already. Who has heard about fractals before? And that's a little bit a pity because fractals are always around us. So everything related to biomimicry is related to fractals. And all of these structures, clouds, mountains, our lung, is a fractal. A tree is a fractal. And they are fractals because what happens is, or the gecko food is also a good example for a fractal because you have a branch and then you have more branches and smaller branches and smaller branches. The agglomerate had the same, right? You had huge branches, smaller, like a tree. And this is a very, very good concept to build structures because they are very light, have a huge surface area, can be extremely stable. And the cool thing is, since the nature is a fractal in all kinds of entities, we directly have a feeling for fractals without knowing it. But we know that, or we are so used to nature, and this is, we are able to detect fractals even without the equation I showed you. There's a very nice example of this, and this is art. So in art, that's a picture for me years ago at the Museum of Modern Art in New York. I was really pissed because normally in the US, most of the museums are for free, but this one is very expensive, and then you pay a lot of money to see this kind of art. And this was why I really was annoyed, because for me, that's not art, okay, but maybe I'm too much engineering, but yeah, I don't know. And this is worth millions, okay? So maybe you should think about your subject. But fractals appearing in art. And one famous and simple example is this one, the wave, which is also, I think all of you know this picture, right? It's an extremely famous picture. And there you see it's a wave, and the same behave or the same shape of the wave is what you see also in the foam, okay? So the structure is the same. It's called self-similarity, but it gets smaller and smaller. And this is something we always see in fractals. So here we have the circle of the wave, and here we have the circle of the foam, and even you could have it even in one dimension larger, and this one we had, but this is an important part. Do you know who made this picture? Actually, I have a project work at the moment running on it to analyze it. Anybody knows who made this picture? This is one of the good pictures in the MoMA, actually, because from this guy they have some pictures. This is a picture from Jackson Pollock. And this is very interesting because Jackson Pollock was a quite crazy guy, but a very famous artist when it comes to modern art. And one property of fractals is something you see very well in this picture, and this is the question, do you see the full picture or do you see only a part of it? If I would zoom in or zoom out, you could not make the statement. Because I could just show you one part of the picture and it would look the same for you. The same is with clouds and rocks, or the coastline of Great Britain, you can zoom in and zoom out, but the patterns are always the same. Okay, so the coastline has a wavy pattern, and if you zoom out, you again on a larger scale see a wavy pattern. So what's now about this picture or Jackson Pollock? So he made his art in the 20s or 1910 or 1920, something in this time. And here I understand why the image or the picture is so expensive. Because what he did is he made just color drops on it, right? So he has this kind of paper and then he just take paint and is doing that. And this is the picture. But the funny thing is that he was very critical about the picture. And he was very unhappy. So he really worked on the technique how to put water or color, on his painting. And he developed a special technique. And a lot of people tried to copy this kind of pictures, and all of you could do the pictures, but it would not be a Pollock picture. The question is why, and the answer is quite simple, because he was able, in the special technique he used, to put the ink on the paper to produce fractals. So his images hold an analysis if this is really a fractal. They are fractals. And since the theory of fractals was not developed at this time, he could not know it. But he always had these, he was looking at the picture and had the feeling, something is not perfect in this picture, I have to do it again. And then he tried out. And at one point, the structure he made is the same as the structure we see in nature, and we have a natural feeling for it. So if you go on a Pollock picture, you have the feeling, okay, something is familiar to me, something works. And if I would do, this is missing. And this is because we have a natural feeling for fractals. And this was basically the worth he was adding to it, right? The theory was not developed, but he had a feeling for it, that there is something, and this is what he's expressing in the picture. And then I understand why this picture is worth millions. Okay, for the other, I still don't understand why there is a worth for this other one. But here is an extremely interesting story about it. And we have this sensor for fractals, and so Pollock pictures is a very nice example for fractals. Good. So we have some problems with TEM, SEM, and then I would like to go to the last technique, and then we are done for today. And this is that we only can take a look at 2D. So the images I showed you are always 2D images of 3D structures. And when you think, for example, that an agglomerate is a three-dimensional structure. We only see a two-dimensional idea of it. Then we need a flat sample, especially in TEM, very thin one, and we need vacuum. And vacuum is extremely expensive and not so easy to handle. And therefore, we have another family of microscopes, which was also awarded with the Nobel Prize. And this is atomic force microscope, and the family related to it is scanning tunneling microscope. And here, and this is why I have my record player with me, so you have a tip, and in the best case, you just have one atom at the top. It doesn't work perfectly like this. Mostly you have a few atoms, and the atom on your small tip interacts with your sample. So you go over a sample, and the tip interacts. How does it interact? Adhesion force. Okay? So there is an adhesion force between the tip and the sample. And for example, you can tell the machine, I want to have a constant force between my tip and my sample. So what happens if you move your needle where the tip is sitting, and then now a bump appears? So you would be too close, so the adhesion force is lower or stronger, depending on the material. And this means if you said, no, I want to have a constant force between my sample and my tip, what has your tip to do? It has to adapt to it. And then now you're losing distance, so the force is too weak, so it goes again. And like this, you can follow each kind of surface. And this is what you see here in the first publication. You see you have an extremely high resolution. Here in the first one, they had lateral resolution of 13 angstrom and vertical resolution of 1 angstrom. So you can see, detect, and image single molecules and atoms, which is extremely important in nanotechnology, right? So generally, it works like this. You have a cantilever, like a spring. With a spring, you can calculate a spring constant, and then you can calculate a force, right? Hooke's law. And you have a tip and a sample. And basically, you move the cantilever downwards till you're very close, and then the adhesion force between the tip and the sample will start to work. And when the adhesion force, doesn't matter if it's adhesive or repulsive, the cantilever will bend. And this bending you can detect by a reflected laser light in a detector, and there you can generate an extremely easy and nice image. And this is in a small GIF. It works basically like this, right? And the big advantage is, a lot of advantages, you don't need vacuum. It works in air, it works in humidity, it works in water, it works in vacuum. So you have all kinds of environment. What is a very big advantage for the AFM? When you don't have to go to vacuum, where could this be extremely helpful? In which kind of research? Which kind of research field don't like vacuum? I mean, for my titanium nanoparticles, doesn't matter if I put them in vacuum or in whatever. That's that's a very broad guess. No, an AFM goes to 30 angstrom. So think about the size scale. So we're talking about individual atoms or small nanoparticles. But what field of research could be, for what kind of research it could be important that you don't have to apply a vacuum? Whom of you would like to be in a vacuum? Whom not? Yeah. So what kind of research? Yeah? Not necessary, because this could be powders. So what, yeah? Yeah, biology, right? So all kind of biotech, biology, and so on, because you don't want to be in a vacuum like all kind of cell, bacteria, virus, or whatever. So for biology, the AFM is an extremely powerful tool. And for other things, the nice thing is you can get these 3D images. Okay, an AFM really gives you, these are particles, these are any kind of structures, and you get really a 3D image. And I would like to show you the working principle, and now we can talk about this very nice device here, because the working principle is exactly the same as what I have here. So you have the sample, this one is the record player, right? And you have the needle, what you see here. This one, the tip, I have a tip here also, right? So the tip is, this would be the cantilever here. So, and on top of the cantilever is a small needle, and the small needle is what you see here as a tip. The only difference is, the tip is 10 nanometer and here it's larger. So the driving force here is gravity, right? The gravity pushes the needle down, and here there is no gravity. So what is pushing the needle down is adhesion. But the principle is completely the same. And if we take a small look, so unfortunately, one thing I'm not so happy is the image there, but the image is not so important. So what you cannot hear is, but I hear it, is the sound. And that's the nice thing. So the machine already makes sound. But I didn't connect it to the speaker. Actually, I don't know if I'm able to connect it to the speaker. I didn't try it. But what you see here is, we have a Python code. Now I have to check where my mouse is. Okay. So, and here we try, or one of the students in the project work, try to kind of explain how a vinyl record works, or record player works. And here would be an image of the record itself. That's not so important, but what you see here is this GIF. And the GIF tells you, you have the needle, and the needle has the same problem as in the AFM. And this means, so the audio information, I'm listening to the information now because I can hear it here, is somewhere in the record, right? So, and there could be two ways. You have heights and depths in audio, and this means you have to have a pattern in the record. And the pattern could be, and this is a very natural idea, is that you have it like this, for example, and then the needle goes along. But the problem you see on the right, and the problem would be if you put the information like this, the needle would jump all the time, and the quality would be extremely bad. The same problem we have in the AFM. So how a record is built up is that this is the channel, and the information of height and depths are here and somewhere here, on the left, on the right, 45 degrees tilted. And this is then, the needle doesn't have any problem, and this is what you see on the left. So it just goes like this, and then it detects heights and depths, and this is how it generates a sound, okay? And what we can do now here is, and that's quite nice, is, if I find my mouse back, is here. So what I can do is, I can run the script. So I put in some libraries, and now I have to put in some basic informations about my record. So what is basically the size of it and whatever. But this is always the same. And now the important part is what comes now, and now I have to be fast. Because what I'm doing now is, so here I have to put three informations. One is the round per minute, and I see it here, it's 33. So this is how fast it rotates, okay? And the second one is the sample rate. And the sample rate is basically the sensitivity of my system. So if I measure over a certain size, a time, and this is the third one, enter record duration. If in 10 seconds my sample rate is 10, I get 10 measurement points in 10 seconds, so 1 per second. So you cannot make a sound of it. So I need a lot of points, enough to have a nice pattern. So, no, I want to have an earlier one. So what I do here now is that I say, okay, so now he's asking, and it's 33. Sample rate is 10,000. That's already a good one. And now for 10 seconds, I would like to record. Okay, now he's finished. You always see it if he's calculating or not. In the top here, there is this sign, and if it's a cent clock, he's calculating. So now he's finished. Okay, this is just data, and now, that's quite nice. That's basically this one is the data he collected. That's basically just the heights and the depth as data points. The same in AFM. The AFM will go the same over a surface, and at the end it will give you a line of ups and down. And it's completely the same like this. But the nice thing is here it's music. So I can tell him, please show me what you recorded. Basically, that's the favorite singer of my mother. So I have to listen to it very often. But it's important for you to understand. So what you were listening at these 10 seconds here, what you are hearing here is nothing else than an AFM would give. So I'm collecting this information as one line, and then I just say, okay, play. And what do I want to do with this information further is, because the AFM gives 3D images, right? So, and how does the AFM giving a 3D image? Now we have to calculate a little bit more with it. Zack, zack, zack. Is he calculating? No. Here, zack, zack. So this is now the line you saw. You just saw a straight line, and now we transferred it into the record. Okay, so you see there are multiple measuring points like going around, which makes sense. 33 rounds per minute, 10 seconds, so should be more than one. But I don't like this image so much. So we made some data analysis more on it. And now he's calculating. It's again calculating. We have to give him some time. Okay, so now it's already a small zoom in, right? You saw this circle where you didn't see much, and now it's a zoom in. It's only part of the information, but you see now a little bit 3D, the the same kind of informations here. And now you see on the top view, which is a little bit easier to see, you already see these patterns, right? And these are the real patterns in the record. And this is the pattern of what you were listening to. This is the music I played, looks structurally in this record like this. And then we could go even further. And this will again take some computational power. And for me, it's important that you get the principle, okay? So the needle goes over the surface, and we can read in this information with a computer. And then we have data points, and we can play around with the data points. We can play the music, and we can generate the image, and the image is nothing else because the data points is an information about heights and depths, and then we can get this one, okay? So this is the 3D image of this record I played here. Okay, so at the moment I showed you a 10-second sequence which I recorded on the laptop, and I generated a picture out of it which shows how the record surface looks for the 10 seconds I showed you. Okay, and this is the exactly same principle in AFM, which costs up to €500,000, generates a picture. Okay, it's a little bit more complicated, of course, but you get these kind of 3D images. And if you look back now in the presentation, right? So these kind of 3D images here, they are generated in the same way as I generated the picture here. The only difference is the size, okay? Here it's the cantilever from the record, and here it's the cantilever from the AFM, and this is how this tool works. Okay, so with this I would like to end the class. No, that's not the correct slide. This is the correct slide about it. So I hope you learned a little bit about the measurement techniques. You see how complicated it is, how important it is to get these different properties depending on what you want to figure out. I hope also I could give you an idea about the fractal dimension. And then we are done with the class for today, and I will see you in half an hour in the seminar. Okay, so thank you.